So welcome back, and next we'll be discussing about the rest of the parameters. So we'll start with the definition of speed, which is another important kinematical parameter. So speed, as you know, is simply defined as the rate of change of distance with respect to time. Okay, so say the rate of distance traveled with respect to time. Now, obviously, when we are talking about the rate of distance traveled with time, we are talking in terms of rate of change. And as we have explored in the subject of calculus, rate of change of essentially a function, where let's say in this case we're talking about speed being the rate of distance with respect to time. So distance would be a function of time. In other words, time being the independent variable, distance would be the dependent variable. So the distance being a function of time, we could define rate of change of distance with time in context of either the average rate of change, which is the total distance in a certain interval divided by the interval of time, or we could also define as an instantaneous change. Now the instantaneous would be a very small change or a very small amount of distance traveled in a very small interval of time, and it would be the ratio of these two, right? So speed, when we talk about average speed, we will define it as the total distance divided by the total time taken, right? But when we talk about something called instantaneous speed, so instantaneous means at a particular instant. So we are talking about a very small interval of time. So we would say it is limit delta t tending to 0. Delta as a bounded. So that would be ds by dt. So here delta s is the distance traveled during time delta. Okay. So while we would define the average speed in an interval of time delta t as delta s by delta t, that is the average rate of change of distance with respect to time, we would define the instantaneous with a special condition that the rate of change we are discussing about is during a very, very small, or what we call an infinitesimal interval of time. So that is limit delta t tending to 0. So that, as you know, is defined as the instantaneous rate of change, or the derivative of distance with respect to time. Okay. So before we get into examples, let us also see that speed is, for example, in terms of classification, speed is a scalar quantity, because we define it in terms of distance and time, and distance and time are both scalar quantities, right? And the other thing being that the dimension of speed is length per unit time. So it's units. The SI unit would be meters per second. CGS unit would be centimeter per second. So that is general thing. Okay. Now the more important aspect over here is that the understanding of average speed in an interval versus instantaneous speed, which is basically defined in terms of average rate of change of distance versus average time. So let's understand that with an example. So given graph of distance versus time. Let's say the distance is given in meters and the time given is in seconds. Okay. So let's say that the particular graph that we've got, it's progressing like this. Right. Alright. So suppose given this graph and we want to find out average speed for 0 to 10 seconds, then to 20 seconds, and let's say 0 to 30 seconds. Again, we want to find out the average speed in each of these cases. So let's take a moment to understand the question here. So as you can see, we are talking about the average speed in a certain interval of time, and to find that out, we have what is basically a graphical representation of distance with respect to time. So using that graphical representation or that visual representation, we will find out average speed using the definition. That average speed is the total distance traveled in a certain interval of time divided by the interval of time. Okay. So pretty simple. So let's see the first one. Okay, now we want to find this out from 0 to 10 seconds. That was the first part of the question. Right. So in 0 to 10 seconds from the graph we can see the distance traveled is 24 meters, right? And the time interval is 10 seconds. So that would be 24 meters divided by 10 seconds. 2.4 meters per second. So that becomes simple answer for the first part. Alright, now similarly, looking at the second part, so we wanted to find out the average speed from 10 to 20 seconds, right? So as you can see, the average speed is distance divided by time. So in 10 to 20 seconds, you can see that the distance remains 24 to 24. That means that extra distance traveled between 10 and 20 seconds is 0 meters. So that is 0. Okay, so as you can see this. So So that is the average speed for the given interval, which basically just shows us that the particle or the body in concern here does not shift from 10 seconds right up to 25 seconds. It just stays at the location it was. Right. Next, let us look at the average speed from 0 to 30 seconds, right? That was the next part. So you can see that is okay. So 0 to 30 seconds is going from here to this point. So the distance traveled is 36 meters and the time interval is 30 seconds. Right? You can see that's 1.2 meters per second. Right, so these are the various different types of calculations we can do to calculate average speed in a situation like this. Okay. Now, next up, in the same situation, we can also see what instantaneous speed is. Okay, so for example, we could be asked to calculate Right, so let's try to understand what instantaneous speed would be from a graphical point of view. Okay. So as we've seen before that the instantaneous speed V, okay, or we can just call it speed from now on. So contextually, when we use the term speed alone without any prefix attached to it, we would be talking about the instantaneous speed. So instantaneous speed is ds by dt, right? Now graphically, okay, geometrically, you can see that ds by dt is slope of the distance time graph, or is what we call slope of tangent. If you remember your calculus, then in context of rate of changes, we can either draw a tangent at a given point on a curve, or we can draw a secant line between 2 points. So when we calculate the slope of the secant line between 2 points, it gives us the average rate of change between those 2 points. So it gives us delta y by delta x, so y2 minus y1 upon x2 minus x1. Whereas when we calculate the instantaneous speed at a particular point, instantaneous rate of change, dy by dx, what we are essentially doing is we are calculating the slope of the tangent drawn at that point, right? So now coming back to this, you can see here that the speed at 5 seconds would be nothing but the slope of the graph at 5 seconds. It would be the slope of this line. So you can see that the slope is basically tan theta for this one, right? So tan theta for this one you can see is delta y by delta x, or 24 by 10, right? So that is 2.4 meters per second. That is, it is the slope of the ST graph at t equal to 5 seconds. So that is the contextual significance of slope of tangent, and that is the geometrical method of figuring out the instantaneous speed at a given point. Okay, so just take that down and we look at the next part at 15 seconds. Right, so similarly you can see here that at t equal to 15 seconds, it's the slope of this line, and you can see it's a horizontal line at this point of time, so that's 0. The instantaneous speed at 15 seconds is 0. And similarly, if we look at the instantaneous speed at 30 seconds. So that's this point here. We want the slope of this line. Okay. So let's say this angle is alpha, whatever. We want tan alpha. Okay. So that is basically again change upon change. So the change you can see is 24 by 10. So that is again 2.4 meters per second. So that is slope. Got it. So I hope that this particular example makes this adequately clear. Okay, the difference between average speed and instantaneous speed. So we will also make a general note of this. Okay, so suppose that is our distance versus time, and at a particular time t1, the distance is s1, and at another particular instant, time is t2, the distance is s2. You can see here that this is s2 minus s1, or delta s, and this here is t2 minus t1, or delta t. So that's slope of secant line. Okay, this sort of a line is called secant line. Right, so just take a moment there and absorb that. It's an important concept. Then we'll talk about instantaneous speed next. So let's say that's our distance versus time graph. Now at a particular moment of time, when the instantaneous distance is s, you want to calculate the instantaneous speed. So what we'd have to do is, we'd have to take a tangent line at that point. Okay. And we have to calculate its slope. So that is the contextual significance of instantaneous versus average in a geometrical constant. So just take a moment to note that down. So this example says that a body covers right. So let's see another interpretation of average speed. Now in this we don't have information about the graph or anything about the instantaneous distance versus time, or speed versus time, how it changes. But what we do know is that we sort of divided the motion into two parts. two intervals of 2 minutes each, and in the first interval of 2 minutes the body is traveling a distance of 20 meters, and the second it's traveling a distance of 40 meters. So from that we have to find out the average speed. Okay, so let's look at the solution of this. So average speed from 0 to 2 minutes is total distance upon total time for 0 to 2 minutes, right? So you can see that that is 20 divided by 2, or say it's 10 meters per minute, or you can convert that, so it's 1 by 6 meters per second. Okay, this dividing by 60, it's covering 10 meters in a minute, so it will take 10 meters for 60 seconds, so that's how that will come out. Similarly, if you look at the average speed for 2 to 4 minutes, that would be the distance traveled for these 2 minutes divided by that interval of time of 2 minutes. So from 2 to 4 minutes, it's traveling a distance of 40 meters in an interval of 2 minutes. So it's double of this. As you can see, it's 20 meters per minute, or 1/3 of a meter per second. So that is second part. The third part, if you want to calculate average speed from 0 to 4 minutes. Okay. Now we're talking about the interval starting from 0 and ending at 4 minutes. So that would be nothing but the total distance traveled in that entire interval divided by the time. So the total distance would be the 20 meters in the first 2 minutes plus the 40 meters in the next 2 minutes, and the interval of time would also be accordingly first 2 minutes plus the next 2 minutes. So as you can see, that will become 60 by 4, or 15 meters per minute. Okay, so that would be 1/4 of a meter per second. So these become the individual values of average speeds in these intervals. Just take a minute to take that down, and then we'll discuss about velocity next. Now we are coming to one of the more important definitions in kinematics, and that is the definition of velocity. Generally we denote it with the symbol V, and as you can see, it's a vector quantity, right? So velocity is in general defined as the rate of displacement with respect to time. So again, since we are talking about a rate of change, we will talk in context of two types of rate of change: the instantaneous rate of change and the average rate of change. Okay? So average velocity, to make it absolutely clear that we are talking about average, we'll give it a different symbol. So that would be equal to the total displacement divided by the total interval of time. Okay. And since we know the total displacement is the final position minus the initial position. So we could just define this as, let's say, that is saying that okay, so just expanding on that definition, when we're talking about an average velocity, it has to be defined in context of an interval of time. So the interval of time we're talking about is from t1 to t2. Then the average velocity is the displacement during that time divided by that time. So obviously the displacement will be the change in position divided by the time interval. Okay. So that becomes the definition of average velocity. Whereas if you're talking about instantaneous velocity, just like we've seen earlier, instantaneous rate of change is rate of change for a very small interval. So it's the rate of displacement with respect to time for an infinitesimal or very, very small interval of time. So we will just define it as the instantaneous rate of change of position with respect to time. So dr is the displacement during an infinitesimal right. So that's how we define the instantaneous velocity versus the average velocity. So very important concept for us over there, right? Now likewise, if we talk about obviously velocity is a vector quantity. Secondly, these are the units, etc., of velocity. One thing we should also make use of over here is that if the direction of motion of a body is changing at constant speed, the velocity is variable. This is something very important to keep in mind, right? Just take a minute to absorb that. Next definition we'll see is that of acceleration. So generally denoted by the symbol E, acceleration is defined as the rate of change of velocity with time. Okay. So once again we define instantaneous acceleration E as the instantaneous rate of change of velocity with respect to time, and we define the average acceleration as the average rate of change of velocity with respect to time. Okay, so again, if we are talking about an interval of time t1 to t2, wherein the velocity is changed from v1 to v2, then the average velocity in that interval would be, rather the average acceleration in that interval would be v2 minus v1 upon t2 minus t1. Right? And needless to say that you can see acceleration is a vector quantity. Its dimensions are length per unit time square, because it is change in velocity upon time, so it's the dimension of velocity divided by the dimension of time. Okay, so obviously one important thing to keep in mind, acceleration is a vector. Secondly, the dimension of acceleration is -2, right? So units meters per second square and centimeters per second square respectively. And now one thing important to keep in mind is that if direction of velocity is changing while speed is uniform, it means that acceleration, which is rate of change of velocity, is not zero, okay? Because the velocity is changing. Why? Because its direction is changing. So for example, in uniform circular motion, the acceleration is non-zero, because once again the magnitude of velocity is constant, okay, but velocity is variable. There is something very important, that when the direction of something changes while it's moving at a constant speed, because the velocity is changing, the body is in fact accelerated. It's not. Alright, so let's look at an example to get this a little bit more clear. So there's a body which has speed of 5 meters per second along a particular straight line. It's moving along this straight line, and let's say something like 20 seconds down the line, its velocity becomes 10 meters per second. So contextually speaking, this is so we want to find the average acceleration just in magnitude from 0 to 20 seconds. So this was the situation of the body initially. Right? At t equal to 0, it had a velocity of 5 meters per second along the positive x-axis, and while it does not change direction in this case, it continues to move along the positive x direction. Its velocity changes to 10 meters per second by the time the time is 20 seconds. So we want to calculate the average acceleration here. Okay. So keeping in mind that average acceleration is this much. So you can see that for motion along a straight line, let's say x-axis, this average acceleration will be along the x-axis, so we can write it as ai cap. So that would be v2 along the x-axis minus v1 along the x-axis divided by t2 minus t1. So we can say that the magnitude of the average acceleration in this case is v2 minus v1 upon t2 minus t1. So that is 10 minus 5 upon 20 minus 0. So that is 5 by 20 or 0.25 meters per second square. So that becomes the magnitude of the average acceleration. Just take a moment to absorb that and take it down. We'll look at another example after that. look at another example. Now in this case, we are looking at a particle in uniform circular motion. Of radius, let's say 20 meters, and time period, say 12 seconds. So here in this particular question, there's various things we want to find out. So find the speed of the particle. Now, because it's uniform circular motion, we understand that the speed is uniform. Then we want to find out the distance traveled in, let's say, 3 seconds. And the average acceleration magnitude in 3 seconds. Okay. So let's take a moment to understand the question before we solve it. So basically it's saying there is a particle in uniform circular motion. Okay, so understanding it better, what does the term uniform circular motion mean? It means that it's happening at constant speed, okay, and it's a circular path at a constant speed. So circular path which is being traversed at a constant speed will always involve a fixed time period, right? Every time it completes one circle or one revolution or one cycle, you can say, of the motion, the time covered will be identical to the previous cycle. So that is why they're talking about a time period and of course a radius. Okay. So again, given in the question is that the radius is 20 meters and the time period is 12 seconds. Okay. And from that we have to find out the speed, okay, the distance from, let's say, 0 to 3 seconds, and the average acceleration's magnitude in 0 to 3 seconds. Let's say these are the various things you have. Okay. Now, what speed are we talking about here? It is the average speed which is equal to instantaneous speed. Which is basically the uniform speed at which it's happening, constant or the uniform speed at which it's happening. Right? So these particular discussions make certain aspects of the problem very clear and easy to understand here. That the fact that it's a uniform circular motion means that the speed is uniform. Okay? So the fact that the speed is uniform or the magnitude of velocity is constant, it means average speed is the same thing as instantaneous speed, right? And in context of that, we now calculate these various things. Okay, so let's look at the solution of this next. Right. So let's say this is a basic diagram of particular particle's path. Okay. So let's say it's here at t equal to 0. So it would be again here at one time period. Again it would come at two time periods like that, because one cycle is repeated every 12 seconds, right? So it would also mean that in an interval of t by 4, 1/4 of a cycle, it will be here. So again t plus t by 4, it will be here. And at 2t plus t by 4, it will be here. Okay. And like that, it will be here at t equal to t by 2, t plus t by 2, etc. It will be here at t equal to 3/4 of a time period, or repetitions of that. So since the time period is 12 seconds, we can see that 3 seconds we are talking about is 1/4 of the time. Okay? So t equal to 0 here, t equal to 12 by 4 or 3 seconds, the particle would be here. So now, first of all, as far as the speed is concerned, it is distance upon time, because remember the instantaneous speed is the same as the average speed in this case, because it's a uniform speed. So it's the total distance upon total time for whatever interval we take. Let's say we take one full cycle, so the distance traveled in one full cycle would be 2 pi r, and the time would be one time period, so that is 2 pi into 20 in meters, right, divided by 12 seconds. Okay. So that would be 10 by 3 pi meters per second, right? So that would be the uniform speed to circular motion. That's one part done. Now the distance travelled in 4 seconds, sorry, 3 seconds, that would be 1/4 of the full cycle, so 1/4 of the time period. So as you can see, that would be pi into 20 by 2, 10 by meters. That's the next important thing here. Just make sure you take a note of that. Right, taking that down, next we'll move on to calculation of the acceleration between the average acceleration, that is, okay, between 0 to 3 seconds. Just take this down. Right then, so moving on to the next part of the question. So you can say the interval of time we are talking about is 0 to 3 seconds, right? So the particle is here at t1 equal to 0 seconds, and let's say t2 as 3 seconds, so that's where the particle is located. Now, keeping in idea simple concept of circular motion, that the velocity is always tangential. So that's the velocity v1, right? And its magnitude was 10 pi by 3. Okay. And at this point of time, this is the velocity vector. Its magnitude is 10 pi by 3. So average acceleration, remember, is change in velocity upon change in time. Okay. So just thinking in terms of a vector diagram, we can see that apologies there. Taking a minute, right? Right. So this being an isosceles right angle triangle, see that this side will be root 2 times the other 2. Right. So magnitude of average acceleration, magnitude of v2 minus v1 upon t1, so that is right. That would be the final solution. So as you can see, the average acceleration from 0 to 3 seconds would reduce to that much in my video. Right, so just take a minute to note that down and absorb that information, and we can move to the concept clearing problems after this. Look at this question next. Alright, so let's understand this question contextually. So just take down the question and we'll discuss about the solution. Okay, so looking at basics, we can do a visual understanding of the problem first. So suppose we take this to be our x-axis just to save time. The particle is here at t equal to 0. It starts with a velocity of starts moving from a point to a point A, a constant velocity of 5 meters per second. Then reaches the point E at time t equal to 5 seconds, continues ahead, reaches the point B at 10 seconds, then rests for 5 seconds. So you can say it rests from t equal to 10 to t equal to 15 seconds. Okay. Then it turns back and it has a velocity of 15 meters per second along the negative x direction, and it reaches the point C after 20 seconds. So it would reach C at precisely 35 seconds, and it would cover certain distance. So let's say this distance is 25 and this is 25, so that's 50. 20 seconds. So let's say C would be somewhere here. Reach here at 35 seconds. Why 35 seconds? Because see, from B to C, once it starts moving, it takes 20 seconds. Okay, it starts moving from B at 15 seconds because the rest is for 5 seconds. So it would reach C at 15 plus 20 or 35 seconds. Okay. Now let's talk about the average acceleration between A and B. Okay. So the first part, the average acceleration from A to B, it would be the velocity at B minus the velocity at A divided by the time interval. Now you can see that once it comes to B, it's at rest, whereas initially at A it had a velocity of 5 meters per second, and the interval of time between A and B is 5 seconds. Right? So 10 minus 5. So you can see that is minus 1 meters per second square. Or let's say it is minus I cap meters per second square. That is the average acceleration from A to B. Right, so hope that part is clear, and we take that down. As far as the average acceleration is concerned between A and C, okay. Okay, so that would be, as you can clearly see, the velocity at C is minus 15 I cap meters per second, and the velocity at A is plus 5 meters per second I cap. The total amount of time from A to C, A to B takes 5 seconds, then it's at rest at B for another 5 seconds, so that's 10 seconds, and another 20 seconds to C, that's a total of 30 seconds. As you can see, this becomes minus 20 by 30 I cap meters per second square. So the average acceleration from A to C is minus 2 by 3 I cap, or its magnitude. So that is another interesting type of problem for you. So now we will be moving on to the concept clearing problems for the first concept which we have discussed here. Okay. Just take a moment to dwell on that, finish that off. Says that a body moves from A to B at a constant speed of 20 kilometers per hour, and then B to C with a constant speed of 30 kilometers per hour. The average speed of the car is how much? Modification to the problem is required. Okay, so I'll put that up on the board. So it says the body moves from A to B at a speed of 20 kilometers per hour. Okay, and this is the modification. Distance from A to B is suppose D. Okay. And then from B to C at a speed of 30 kilometers per hour. Or let's say from the distance from B to C is also equal to D. Okay. So the distance from A to B is equal to the distance from B to C, and let's say that is some D. So you have to find the average speed for the motion from A to C. The composite motion, okay, taking the whole interval from A to C, you have to calculate the average speed. Let's work that out. Okay. So, as far as the solution is concerned, see that average speed is total distance upon total time. So that will be the distance from A to B plus the distance from B to C divided by the time from A to B plus the time from B to C. Right. Now the distance from A to B is equal to the distance from B to C, which is equal to D. Right. And A to B is happening at a speed of 20. Right. So the time will be 20 divided by, the time will be D divided by 20 for A to B, and similarly B to C it will be D divided by 30. Okay. Assuming that D is in kilometers, so this will be in kilometers per hour, right? So you can see this will become 2 upon 1 by 20 plus 1 by 30, 2 into 600 divided by 20 plus 30. So that is 1200 divided by 50, 120 divided by 5, so that is 24 kilometers per hour. Right. So this is a significant, important type of question. Right. Let's take this now. As a particle is moving in a circle of radius r with a constant speed, we have to find the change in velocity when it has traveled a distance equal to 1/8 of the circumference. Okay. So not only will we calculate the change in velocity, we will calculate the average acceleration during that interval. Okay, so let's do this. So uniform circular motion. Radius r and speed v. Find the magnitude of change in velocity and magnitude of average acceleration during 1/8 of a cycle. Okay. So let's understand the question thoroughly once. It says that we have a particle in uniform circular motion with a given speed and radius, and we want to calculate the magnitude of the change in velocity and the magnitude of average acceleration during an interval of time when it has traversed 1/8 of a full circumference. Right. So let's understand the question geometrically. Looking at the solution of the problem, see, this is the circular path. Now the particle is somewhere here, let's say at t equal to 0, and it's somewhere here at t equal to t1, let's say, and this angle is 1/8 of, or it is pi by 4 radians, 45 degrees. So the velocity of the particle at this point of time would be this. Its magnitude would be v, and the velocity of the particle at this point of time v1. Its magnitude would be again v, which is given to us. Okay. So the change in velocity would be magnitude of v1 minus v1, right? So now see here that this angle would be the same here, right? So this would be theta. That would be our delta v, right? So delta v's magnitude would be square root of much. Theta being 45, right? So right, so that would be the magnitude of change in velocity. And now, if we also want to calculate next the magnitude of change in acceleration, or the magnitude of average acceleration, see that t1 would be 1/8 of one time period, so that is 1/8 of 2 pi r by v, right? So that is pi r by 4v, that is the time. So magnitude of average acceleration, the magnitude of change in velocity divided by the time. So magnitude of change in velocity we had just seen was v into square root of 2 minus root 2, and time is zero. And also verify that dimensionally speaking, v square by r has the dimension of velocity. Right? How was that? Right. So we will continue with more problems after this. Okay. So continuing ahead with the concept clearing problems. Next, we will look at the 10th one. So this problem says that a body is traveling with given velocities in successive intervals of time, and we have to find the average velocity. Okay. So 10th question says that body travels at velocities of v1, v2 and v3 in 3 successive intervals of time t each. Calculate during the motion. We have to calculate the average velocity. Okay. So pretty simple. We look at this as apologies. We have to calculate the average speed. Okay. So that is total distance, total time, right? So that becomes a distance of v1 t for the first interval, followed by v2 into same time t for the second interval, followed by v3 into t divided by the total interval of time. So that is v1 plus v2 plus v3. Right, so that's the solution for the 10th problem. Right, so let's also pick up a question or two from the exercises. So let's look at the 4th question of exercise 1. So it says that a body completes one round of a circle r in 20 seconds. So we have to find the displacement after 45 seconds, right? So the body completes a round of circular motion every 20 seconds. So find the displacement in 45 seconds. This is essentially a question like this, that body is in circular motion like this. Let's say it starts at t equal to 0. So every t seconds it comes back like this. So the given interval of time is 45 seconds, okay, whereas the time period is 20 seconds. So comparing these two, we can see that delta t is equal to 2t plus t by 4. We can see that 45 can be written as 2 into 20 plus 20 by 4. That's 5 seconds. So this is one time period. That's the way it is. So, as you can see, it's back here at 2t, and then another t by 4, it will be here. This is where it will be at t equal to t by 4, then t plus t by 4, the next 2t plus t by 4. So this is the one we are looking for. So the displacement we are talking about is this. Okay. So the magnitude of the displacement will be root 2r. Right. So hope that little question there from exercise 1 is clear to all of you. Let's pick up some more questions. This is question number 2 in exercise 4. So this is velocity versus time graph body. Moving along a straight line. So find the acceleration at t equal to 10 seconds. So let's say we want to find the instantaneous acceleration at t equal to 10 seconds. So we can see that the instantaneous acceleration is instantaneous rate of change of velocity with respect to time. It's a one-dimensional motion, so we've reduced the vector equation to a scalar equation. And from that we can see that that is the slope of the tangent at t equal to 10 seconds. So that would be tan theta. Here you can see theta is this angle, so that's 120 degrees. So tan of 120, as you know, will give us minus root 3. So that becomes the solution to this. So that's just a brief example. So that concludes concept 1, discussion of problems.